using digital radiography, computed radiography. Right now, everybody, it's two terms. Computed radiography is when you're using the imaging plate in a reader, and then digital radiography refers to the detector being incorporated in the equipment like we have in the front room. Okay, so that's where we're at the moment. The CR is going away. This was the best thing we could have done to convert to digital radiography, a digital image on the monitor. So this allowed us to incorporate our already the X-ray rooms that were already in use. So all we had to do was add a reader and a computer and these cassettes, and then we were able to take our film images and make them on digital, put them on a computerized. Okay, so what we had, let me just give you a little brief history. What we had before, Wilhelm Conrad Röntgen took an X-ray on these, and you have to be real careful. Glass plates. I've not ever seen this before until I came here to Cypress College. And you can see, can you tell, I know, what's the issue with glass? There's tape around the edges.
Very fragile.
There's tape around the edges so you don't cut yourself. The hazards of being a radiographer. It's glass, so they do break. This one is from 1920. So what it was a high quality piece of glass with the emulsion coated on it. So you don't have a view box to hang it up in. It's too thick for that. So I guess they just held it up to the light. I'm not that old, I don't know. I know I've been in the field for a long time. So that was glass. And then we very quickly evolved to cassettes. So here is a DuPont cassette with screens mounted on the inside. These are the screens. This made the biggest difference in patient exposure. As I said before, you can greatly reduce. These are screens that take X-ray energy and convert it to light. And so it takes very little X-ray energy to produce a lot of light. So we were able to drastically cut down our X-ray exposure to the patient. Now the problem with the screens, anytime you involve light, and you're going to learn about this in digital, it's the same for here and it will be for digital. The issue with any time you convert to light, do you know what light does? Come on in. How are you doing? Do you know what light does? As it goes any distance, it diverges, it spreads, and that decreases detail. So I showed you, did you see this? Did anybody care to look at that? Did you see that cardboard? Was that not exquisite? Okay, but the price is too high. The price is too high as far as exposure goes. So that's what the screens did. These two are screens. Is it bad? No, compared to that, yes. But you still get good detail. And we have different screen speeds, as you may have remembered from intro class. Slow speed for better detail, high speed for bigger body parts and where detail wasn't as critical. You would put a piece of film in here, and in the dark room you have a light tight container. You have a tube side just like the cassettes you have now for CR. Make the exposure and put it through a processor, and you have a piece of film. You can make the best X-ray possible. It could be a beautiful X-ray, but you put that film in a processor and you cross your fingers, because the processor, they have books on what can troubleshooting a processor. They tear up the films if the rollers aren't right, if the chemicals are too hot, if the concentration's not right, if the filter's not working, if the darkroom lights aren't appropriate, if the darkroom lights are too close to the tables. I could go on and on and on with horrors of processing. One time, we are in the night shift or working ER, lots of things going on, and the water got turned off. I mean, you have no image until you have a processor that can process it, and it requires water and electricity. So lots of problems with this, but it was great in terms of reducing patient exposure. And there's different cassettes, all different kinds of cassettes and manufacturers. This is actually Gavert, never heard of them until I moved out here to California. DuPont I'm used to, Kodak. So again, these are gone. And so now we are now here. The other issue is with these cassettes and film is that the film once, lots of things could affect film. If you expose it to light, expose it to excessive heat. I had a box of film that the expiration date was over and it was fogged. Lots of things that can go wrong with film. So it's nice with these cassettes, these CR cassettes, is that they have a cassette. The cassette is only to support this. It doesn't protect it from light or anything like that. Unlike these other cassettes, protect the film from light. You load it in the dark room. And here, these are just fit in here, and the light doesn't expose it. Okay, so that's what's nice about the CR cassettes. Has a barcode on it. Before we had to flash the patient's name onto the piece of film with a flasher. So that's what these little windows are. See this? So what happens, can I borrow your pencil?
Sure.
What happens is either you put this in the patient's name is on a card, put it in the reader, put this in there, it opens up this little window and exposes it with a light bulb actually. Flashes light and the patient's name is now exposed on that corner. It closes this up, you take it out and go to the darkroom and process it. So instead of that process, I would show you that, but I threw them all away. Now we're barcoding the information, and so that's pretty much where we're going now with putting our patient's information onto the image. Again, you can take the best image possible, exquisite, so proud, you know, go into the Bontrager book. But if you do not have the correct patient's name on here, it's useless. So your paperwork along with your imaging, and I'm sure Dr. Fernandez has probably lectured you about that, connecting the patient information to the correct image is just as important as getting a good image. As I said, it doesn't matter what your image looks like if it doesn't have the right information on it. So it's extremely important. So this CR came about, and it was really great in my career to see this transition like that. And so this was probably early. Let me just back up. The biggest problem with X-rays were the X-ray department was the last one to be computerized. CT was computerized, fluoroscopy, ultrasound, nuclear medicine, CT, all computerized, but not radiography. These images take up a lot of computer space. Okay, do you remember the CDs? How you maybe could put 1 or 2 or maybe 4 if you were lucky pictures. You take a picture with your camera and then you want to put them on a CD. Am I going too far back for some of you ladies? Okay. And you could only, do you remember that? Anybody? You could only put like just a few on there. And now we're even, forget the CDs, we have the pen drives and you can put, you know, a lot of images on it now. Well, it was the same way with X-ray. Too much information, we didn't have enough storage drive to hold it all. And so it took finally to where we can now store large files, you know, on our computer disks now. So that was the holdup. And so now we're able to replace our film, replace our view boxes and our processors. And this is what the radiologists are doing now. They've got these big, fabulous monitors that they look at the images and dictate now. So this is gone, bye-bye. Never thought I'd see that day. But so now here's an imaging plate reader, and you still have these at some of your hospitals. Quite a few of your hospitals will still have maybe one reader, one CR reader. So Anaheim Regional and Anaheim Global, maybe in Whittier, still have full CR, and they're working towards transitioning to DR. I mean, I think I told you this before, that if a hospital wants to get reimbursed by the federal funding for like Medicare or Medicaid, then they're having to go to DR. So now hospitals are being forced to do that. Mammography legally cannot be taken unless it's digital. So it's really been a lot of changes with that. And I would say it wasn't until the late 80s, early 90s that we were able to transition with the amount of storage capabilities that we have on our images to be able to save them onto the computer. And then, of course, at that point, it took time. I think St. Jude's was one of the first to, you're my hero. I love you. Okay. Yuck. Yay. I got to, okay, we can't have a crummy looking trash can in our beautiful room. Oh.
Yeah, just enough money in the budget for 2 trash cans.
Can you get what? A Starbucks?
Yeah.
Oh, sure, I'll put in for that, yeah, Starbucks. I would love that. Not a problem for me. Okay, so as I was saying, St. Jude was one of the first hospitals to convert to CR in this area, affiliated with us. And I asked the director at the time, what was it that propelled him to do that? Because it was very expensive. And we have read studies, controversial studies, saying that, not having to pay for film, not having to repeat, not having to, buy processing chemicals and stuff like that, that it offset the cost of CR. And it didn't. He said it absolutely did not. So I said, well, then why did you do it? And he said, because that's what our patients expect. The patients were demanding that. In a hospital like St. Jude, we are going to provide them with top-notch, up-to-date caliber equipment. So it was, that department administrator felt like they were pressured to do that because of the patients demanding that. And so now everyone's doing it, and now the transition was all CR, then a little bit of DR, and now we're going fully DR. So we're working our way there. So as you know how to work the CR, so I'm going to run through this real quick, and you can read about it on your PowerPoint. But what is on this imaging plate is, and this is a cassette, we still call it a cassette, but the imaging plate itself, the imaging plate itself is this. So this is coated with a barium fluorohalide, okay? And so this is a phosphor. Okay, so when x-rays hit phosphors, there's all different kinds of phosphors, all different kinds. Some are better at taking x-ray energy and converting it to light. We call that the DQE. Have you heard that, detective quantum efficiency? Anybody? Okay, we'll talk more about that later. But this one, it says it acts like a 200 speed screen. Depends on what manufacturer, but I would tell you that's probably a slow to a medium speed screen, if that means anything to you. So the image is captured on here using the phosphor, just like we did before with light, and then it's read into the reader. There is a photo multiplier tube. It takes that light. This goes into the reader. A red laser light makes these phosphors glow. They capture the X-ray energy.
Stores the energy, right?
It stores the energy, and then when the red laser light hits it, it releases the light. And then a photo multiplier tube takes that light and converts it to electrons, and that's what makes up our image in a nutshell. And then this plate is erased. How we erase this, or how it's erased, is with a white light. Okay, so there's a white light in the reader that it goes through as it's coming back out to be put into the cassette. So we still have that roller system, and these do not last forever, and they can get scratched just like the film and the processor can get all crunched up and scratched and that sort of thing if the rollers are not properly set, if any debris that may be on this that gets into the reader. So scratches can occur, and they do occur. So anytime you have something going through a set of rollers, it's eventually going to get ruined. So here's just a picture of it as this imaging plate is going through. Again, the rollers. Here you have the red laser light stimulating. The phosphor here glows in the blue spectrum. That blue light is picked up by the photomultiplier tube and converted to electrons, which makes up our signal to go to the computer. And here, tests are done. The expectation is that the phosphor would be evenly dispersed over the plate and that it would be even throughout. And we're going to talk about QA later on in the semester. But you would expect these numbers that are being read to be fairly close to each other. So you want even exposure throughout the imaging plate. They came to clean it. It needs to be cleaned every so often. And so I took pictures of it as it was opened. I don't know why I felt compelled to do that. Here's one of the, I think this is one of the lights. This is a light bar. So again, those need to be cleaned. We don't want any debris on the light bar or any of the parts that would uptake the image. So this is the back of it, I think. And again, you see the rollers, the pulleys for that. This is a lot more complicated than it looks. Not something I think I could repair very quickly if something was wrong with it. Isn't that the truth? I mean, I can take a processor, fix it, clean it, put it back together. Right? IP reader, we got a call. What do you do if your IP reader isn't working right? What's the first thing you do?
Tell you.
Don't come to me. I'm talking about for future. If I'm not there to hold your hand, what do you do?
You'll love tap.
Yeah, a little love tap. Okay, so the equipment that we needed, of course, as I said before, was an imaging plate reader and the computer monitor to look at our image. So that's what we needed. This is a multi-plate reader. Isn't that nice? We didn't get one of those. Multi-plate reader where you can put in several out instead of just waiting for it one at a time. And then this is a teacher talking to their students now. Instead of hovering around an illuminator, we're going to be hovering around our monitors in the back now. So here are the imaging plate layers. I do want you to know this, just like you used to have to know the layers of film, now you need to know that. Is this familiar? Is this coming back to you a little bit from 146? A little bit? Okay. Just go back and read about it and just review it. It'll come back to you. This is the phosphor. There are phosphor crystals in there. They have a binder, kind of like a gelatin to hold them together. You have your protective coat. You have a reflective layer. What the reflective layer does, it keeps the light going in this direction. It reflects the light from the phosphors. The phosphors emit light in all directions. The reflective layer redirects the light towards the reader, towards the photomultiplier tube, as opposed to coming towards the base where it doesn't do any good. So every time we lose light, we lose the ability to take x-rays and convert to light. So here's the base, of course, for support, and then an anti-static layer. You can imagine if static electricity were to get a hold of the plates, then it would cause a discharge, and you would not get an image in that area. The pixels wouldn't be activated. And then some lead for what's the lead for?
Absorption.
Absorption of what? The lead is towards the back.
For any like leakage radiation or
What kind of radiation?
or scatter.
Okay, specifically what kind of scatter? So here the x-rays go through the patient, hit the the imaging plate, and then, do they go through the imaging plate? Do x-rays go through an imaging plate? Absolutely. X-rays are very penetrating and will go, not all x-rays are absorbed by the phosphor and converted to light. Some will go straight on through and hit what's underneath. The Becky tray, and it'll hit that high atomic number and backscatter. So backscatter will come across. If you're doing a cross table, so your patient's laying on the table, your x-ray tube's out here and you're doing like a decubitus, x-rays hit that wall and will scatter back towards the image receptor. And you'll be able to see the hinges and stuff like that on the back. So that's why it's lined with lead. A little bit of lead. These were two. These have lead in them. Wait. See? Right there, that's the lead on the back of this screen.
It absorbs the backscatter?
Mm-hmm. Yeah, it's just a real thin piece of lead. Can x-rays go through lead? Absolutely, but backscatter is weak, and so lead is good for backscatter. Your lead aprons, I think I've already told you this before, right? I'm trying to rip it up. I know I'm more worried about my nails than I am the cassette. Here's the lead. This is the lead. Okay, and so it's just a real thin layer because backscatter is is weaker than the primary beam. Any scatter is. And your lead aprons are for scatter only. If you have your lead apron on and x-ray beam's pointed at you, it'll go right through that lead like it wasn't there. So it's not impervious. But anyway, that's the purpose of the lead here. Oh, and here is just a breakdown of what each one does. So eventually when you have your test on this, I will ask you what is the purpose of the protective coat. You hope I asked that one, right? What's the purpose of the binder? What does the reflective layer do? That sort of thing. So make sure you know these, okay? This is all throughout our intensifying screens and also with our imaging plates. When the crystals, the phosphor crystals are round, the light will spread in all directions. But here, if the phosphor is grown in a needle-like column, then the light doesn't spread as much. It's more needle-like. And so less light spread. So if we have less light spread, what happens to our image quality?
Better detail.
It's better detail. It increases. That's right. It sure does. This is another thing I wanted to show you. We talked a little bit about sensitometry. Remember the characteristic curve, and it told us whether a film was fast or slow speed. It told us whether a film had more shades of gray or whether it was more black and white based upon the manufacturer making it. So this is our characteristic curve. And you can see, remember the straight line portion was our useful density ranges, and it was like 0.25 to 2.5. Look at computerized radiography. We have from 0 to 10,000. The useful ranges are here, much more so than here. So that is why you can almost use any technical factor, and it puts, within reason. You can get too low, you can go too high, but even if you're just somewhat close, this is the amount of area your images will come in. So the computer has such a wide range of useful densities. Again, film, I said 3 or 4, 10,000 over there. So that's the difference between CR, a big difference between CR and film. So you have a wider margin of error, I guess, a wider margin of useful densities. And that's where we're going to stop today.